All right, so I want to go over the Chapter 22 problem solutions. Again, sorry this was taken with my phone, so the photos aren't exactly the best, but hopefully it's okay. In this particular case, this is number 12. It gave you a lot of information that was in purple. That's supposed to be 1 amp right there. So you can use the Kirchhoff's junction rule to figure out the current in part B and part C. So in part B, I have 2 amps coming up here, but 1 amp going down this way. How do I know I have 2 amps going up there? Because it's not listed. Well, I have 5 amps coming in from the left, 3 amps going down to the right. So therefore, I must have 2 amps going up to the right. So at this junction, if I have 2 amps going in and then 1 amp going down to the right, I must have 1 amp going through B. For part C, I have 1 amp going into C from above. Here I have 3 amps going down, that was given, and I have 2 amps going out to the right, that was given, so therefore 1 amp must be going up and to the right. So I have 1 amp coming in from above, 1 amp coming in from below, and the current through C must be 2 amps. That again is Kirchhoff's junction rule. For 23, I ended up having, it was basically asking you the length of the wire, so it was giving you the wire diameter. I immediately converted that to radius. I immediately converted that to standard units of meters. So it was copper wire, so I went to the table in the book that found me the resistivity of copper. 1.7 times 10 to the negative 8th ohm meters. The area, pi r squared. 4.91 times 10 to the negative 8th square meters. I rearranged this to solve for length. How did I get the resistance? Well, I was given the voltage across the wire and the current through the wire, so I rearranged Ohm's law to solve for the resistance. So if I know the resistance, the area, and the resistivity, I can find the length of the wire. That was around 8.66 meters. For problem 34, it was asking you to draw a potential versus position diagram. I think this is similar to one of our conceptual questions. Starting just below the negative end of a 9-volt terminal of a battery, and go all the way around, there's 2 light bulbs with identical light bulbs, so they're identical properties. So as I go across the battery, I go up. It really should be, say, 9 volts right there. Let me see if I can say that. Ugh. Let's see if I can adjust the color. That looks nice. I don't like that font. So 9 volts would be like right up here. Okay. And so then after it's passed through the battery, if it's an ideal wire, no change in voltage. Going through the first bulb, we drop down 4.5 volts. Going through the second, then a little bit of space, then dropping down the second bulb, drop back down to 0. And this is at 0 until we get to the start and finish point just below the battery. We went over some of these in class for 40. It gave me the current, gave me the voltage. I think from an electric eel, it said 1 millisecond was the time that the voltage was impressed by the eel. So then at first I found the power. That was just V times I. That's 360 watts. That means 360 joules per second. So to find the energy that the eel gives off, I take power times time. So that's 360 joules per second times 0.001 second. That was 0.36 joules. And then finally, to find the total charge that the eel gives off, I know it was 0.80 amps. That tells me it's 0.80 coulombs per second times 1/1000th of a second. It gives me 8.0 times 10 to the negative 4th coulombs. If they want it in charges, I can convert that. 1 charge is equal to 1.6 times 10 to the negative 19th coulombs. So that gives me that many charges. 5 we went over in class. Annoyingly, I sort of squished it over here for part B because I forgot initially to do part B. So the diameter of the wire was 0.04 millimeters. The radius was 0.02 millimeters. That radius is 2 times 10 to the negative 5th meters. We're really asked to find the length of this wire. It's tungsten at 1500 Celsius, so I go to my table and I look up the resistivity, which is at this temperature 5 times 10 to the negative 7th ohm meters. Calculated the area up here, gave me the power, gave me the voltage, so I can use one of several ways to find the resistance of the wire. That wire was 360 ohms of resistance. So then I rearranged to solve for length, much as I did in an earlier problem. Resistance times area divided by resistivity gives me about 0.905 meters. Now, if it says, what if the tungsten is cooled down to 20 degrees Celsius, what would its resistance be? Well, I'm going to rearrange the formula back to this initial form, which is over here. The new resistivity is 5.6 times 10 to the negative 8th ohm meters. The length I'd gotten is 0.905 meters, so again, sorry, that squooshed, divided by the cross-sectional area, which didn't change. That gives me 40.3 meters, or 40.3 ohms. So the resistance for the same length of wire goes down significantly at a lower temperature. For problem 66, it's the last one, the current through a 1.0 ohm resistor is shown. It's asking about the total number of coulombs. So I screwed up because I said it was 2.5 amps times 3 seconds, and then I said 1.5 amps times 7 seconds. That was wrong. That's a 5-second interval. So I should end up with 18 coulombs. I should end up with around 30 joules here because it's 5 seconds instead of 7. I use P equals I squared times R for power, and then I figured out times time. So if you thought of this as 1.25 amps down here instead of 2.5, your answers would be slightly less. And I hope that helps to go over some of those. I will try to figure out a way to scan these on the machine a little bit better and in the future so it's not from my phone. Thanks.